Welcome, everyone, to this academic masterclass. Today, we're diving into a truly fascinating explainer focused on designing buildings that actually work in perfect harmony with nature rather than constantly fighting against it. Think of me as your guide today through the incredible physics and design strategies of passive energy efficiency. We're going to explore how we can drastically increase the energy efficiency of our structures without just relying on active, power-hungry mechanical systems. By the time we're done here, you're going to see architecture in a whole new light. Not just as static, dead structures, but as dynamic systems interacting directly with their environment. All right, here's our syllabus for today's explainer. We'll be going through 1. Principles of energy efficiency, 2. Site planning and landscaping, 3. Optimizing the building form, 4. Engineering the building envelope, and finally, 5. Smart materials and fenestration. So let's jump right into Section 1, Principles of Energy Efficiency. This is all about working with the climate. This is really where our whole journey begins. Before we even think about pouring concrete or laying a single brick, we absolutely have to understand the core of passive design, and that is bioclimatic principles. Basically, these are design strategies that deliberately use natural elements and the specific micro and macroclimatic conditions of your building site to achieve thermal comfort, and by extension, incredibly high energy efficiency. What we're doing here is shifting the heavy lifting of heating and cooling away from artificial grid-tied power sources and handing it over to smart, intelligent architectural design. Moving on to Section 2, Site Planning and Landscaping. This is your very first line of defense. Okay, so let's follow a hypothetical ray of sunlight as it makes its initial contact with the property, way before it ever hits our actual walls. Proper landscaping can physically block direct sun from baking your building surfaces, and it can even create highly advantageous airflow patterns around the structure. Vegetation is an incredibly powerful tool for this. It literally drops the air temperature right next to the building. Take deciduous trees, for example. If you plant them around a building, you get this critical leafy shade during the blazing summer, but because they drop their leaves in the fall, they beautifully allow the winter sun right through to help heat the building when you actually need it. Location matters a ton, too. Placing water bodies near buildings acts like a giant thermal regulator, smoothing out those drastic temperature spikes. And finally, if you're designing for a cold climate, your orientation should be slightly east of south. Why? Because it grabs the absolute maximum amount of solar heat due to the longer duration of exposure. Check out this diagram. It brilliantly shows how we can use the site itself as a mechanical tool. In this earth tube system, instead of just sucking hot summer air directly into a building, ambient air is captured, filtered, and then routed underground through a long tunnel. Because the Earth maintains a much more stable temperature than the surface air, that air is naturally cooled as it travels through the ground before a fan finally pulls it into the living space. The hot air is then vented straight out the top. It's just a perfect, tangible example of taking advantage of the site's natural microclimate for thermal comfort. Section 3, Optimizing the building form. We're entering the meso level here. So we've optimized the land. Now, what actual physical shape should the building take to maximize all these natural advantages? The most crucial thing to grasp here is the underlying mathematics of the space. The volume of air inside a building that you actually have to heat or cool is directly related to the surface area of the envelope that encloses it. In physics and architecture, we call this the surface-to-volume ratio. This physical shape isn't just an aesthetic choice. It directly affects thermal comfort and energy consumption. It literally dictates how efficiently a building either holds onto its heat or sheds it. Building right on that mathematical relationship, the specific form of the structure determines the airflow pattern directly around the building itself. This is vital for increasing ventilation and overall thermal comfort. But wait, there's more. The actual depth of the building acts as a natural lighting strategy. A highly optimized building depth drastically reduces and sometimes even eliminates the need for artificial lighting during daytime hours. And as you can guess, that cuts energy consumption significantly. Let's look at Section 4, Engineering the Building Envelope, the outer shell. All right, our ray of sunlight and our gust of wind have made it past the trees, they've crossed the water features, and they are now slamming into the outer shell of our structure. The building envelope requires very different engineering strategies depending on the surface we're talking about. Let's contrast roofs and walls for a second. The roof receives incredibly intense direct solar radiation all day long. So depending on your climate, we can apply specific roof treatments, things like removable shading devices, or even green, vegetated roofs to stop overheating in the summer while actually providing a layer of thermal insulation for the winter. Now, walls, on the other hand, absorb huge amounts of solar radiation simply because of their massive upright surface area.
To fight heat transfer through walls, we rely on strategies like carefully adjusting the wall's thickness, building air voids directly into the masonry, and applying specialized surface treatments.
Let's look at a really practical application for a roof. Utilizing mechanical but completely passively driven devices like this roof turbine can massively reduce heat transfer. By simply catching the natural wind blowing across the roofline, it actively spins to vent out the hot air that gets trapped in the upper levels of the building envelope. This helps naturally cool the volume of air below it without drawing a single watt of electrical power. How cool is that? And to visually anchor that wall strategy we just talked about, take a look at this remarkable perforated brick wall. Remember when I mentioned incorporating air voids? Well, this construction technique uses negative space, the literal empty gaps between the bricks, to drastically drop the overall thermal conductivity of the wall. Less solid material means less direct solid-to-solid heat transfer through that massive surface area, which keeps the interior shaded and comfortable. Finally, Section 5, Smart Materials and Fenestration. We've reached the micro level. Down at the micro level, the elements are finally pushing into the living space, making your material selection absolutely paramount. As designers, we must choose materials with low embodied energy, which just means it didn't take tons of burning fossil fuels just to manufacture and ship them to the site. We also need materials with low thermal conductivity and appropriate thermal mass. Thermal mass refers to using dense, heavy materials that absorb and release heat very slowly. And in cutting-edge green building today, we're even seeing the use of phase-changing materials. These are advanced, high-tech materials that act as passive temperature regulators by literally absorbing massive amounts of heat as they melt, and then releasing that heat back into the room as they solidify. It's like having a thermal battery built right into your wall. Now, let's move on and see how all this builds into our final major concept for today, fenestration. It sounds like a big, intimidating architectural term, but fenestration is simply the strategic arrangement of windows in a building. However, we don't just punch holes in walls randomly. It is done with the highly specific goal of elegantly intercepting the solar heat source and passively ventilating the space. This beautiful interior shows off intelligent fenestration perfectly. The location of your windows must be determined by looking at the prevailing wind direction of the site. By strategically positioning large windows on opposite walls from one another, the design drastically increases natural cross-ventilation. At the exact same time, it floods that optimized building depth we talked about earlier with natural daylight, almost entirely wiping out the need to flip on a light switch during the day. But, fenestration is definitely not just a modern concept. Look at these historic wind catchers. They are absolutely brilliant, and they apply the exact same bioclimatic principles we've been unpacking today. By arranging these specialized window-like vents at extremely high levels, they naturally catch those prevailing winds to force heavier, fresh air down into the building while simultaneously venting out the lighter, hot air from the living spaces below. It is just a stunning historical masterclass in passive design. So, we've journeyed all the way from macro landscaping choices down to the micro-engineering of air voids and window placement. And really, it all comes back to a single, unifying philosophy: utilizing natural conditions rather than fighting them tooth and nail. As we wrap up this explainer, I want to leave you with a question to apply to your own everyday life. Just look around the room you are sitting in right now. Look at your own home. Where is the sun hitting it at 2 p.m.? Where does the wind naturally want to flow? Is your home fighting the climate, or is it working with it? Thank you so much for joining me for this masterclass today. Keep observing the world around you, keep learning, and I'll see you in our next explainer.